Okay. So Alex is going to pick up where he left off in his talk in the bootcamp workshop. In bootcamp, Alex presented what, or a subset of what Ale talked about earlier, and now Alex is going to tell us about PHP in the standard model.
All right, hey everyone. I will also be picking up after where Ale left off just now. So today I'll give a tutorial on how to sleep at night. Current state of the art and future challenges on sleeping at night. All right. And what I would like you to get out of this talk is on the next slide, and then we can all go home. You can skip the rest of the talk and skip the rest of the day. I don't know. But all right. So here's a flow chart. If your question is, or if your starting point is, I know it's not readable with this text size, but this says, I want to Fiat Shamir compile a protocol. And here is a flow chart which will tell you what you can do or not do based on the current state of the art. I mean, this is the entire point of the talk. Please don't try and read this right now. But if you want, the slides will be up somewhere after the talk, and maybe this flow chart will be useful to you. Yeah, but there is a flow chart, and this is already maybe a good thing for us. And it tells us like what we already know how to do, and there are a few. We've got research problem over here, research problem over here, and hard research problem over here. So we have a flow chart which 3 times ends with research problem. All right. Okay, so now I'll start the real talk. So the entire workshop is about proof systems, and to grossly oversimplify, there are 2 things that we often look for out of a cryptographic proof system. One is that we would like the prover has some secret that they would like to hide from the verifier. The best possible security notion you can achieve for this goal is called zero knowledge. And the other thing that we like to do is we like to save the verifier work. We'd like verifying to be much faster, much more efficient than deciding whether or not the original statement was true. And when we do this, we say that we have a succinct argument system. Amazingly, in this interactive protocol model, that is, if you allow the prover and verifier to exchange messages, then we have known how to achieve both of these goals for a very long time. We know how to build zero-knowledge proofs for NP under very minimal computational assumptions. What you need is a commitment scheme, which we can build from one-way functions. If you want a succinct argument system for NP, we know how to do this, also under a very mild hardness assumption. So using a very easy to construct cryptographic primitive called a succinct commitment scheme. Ale's talk was a lot about this. Okay, so this is wonderful. And just to have like 2 running examples in your head for the rest of this talk, I'm not going to spend a lot of time talking about them, but I'll at least flash them in front of you. So whenever I say take your favorite interactive protocol, I would like you to pick one of these 2 protocols. Like I'm being very reasonable. I'm giving you 2 choices. One of these should be your favorite protocol. All right. So here are 2 running examples to keep in mind for the rest of the talk. So in a committed open protocols are what Ale talked about. I'm just showing a 4-message version of committed open here, although you can have versions with more interaction. And so the general shape of this protocol is that the prover generates some proof string pi and then commits to it, sends this commitment to the verifier. The verifier then samples some sort of query set S, which is pointing to which is referencing some subset of the bits of the string pi. And then in the protocol, the prover has to open the locations of pi corresponding to the verifier's query set S. And then the verifier will check that the opening is valid, and then check some property of the string pi sub S. So this is not a fully specified protocol, but a lot of protocols look like this. Okay. And indeed, you can use this protocol template to get both of these classical results on zero-knowledge proofs and succinct arguments. Yeah, in particular for succinct arguments, this string pi is exactly a PCP string, and the set S is a query set for the PCP. All right, so here's one running example to keep in mind. The other running example to keep in mind, especially if you want to think about multi-round protocols as opposed to like two verifier messages, is the subject protocol, which underlies a lot of what's going on in succinct arguments anyway, and the PCP theorem. So in the subject protocol, the instance is the description of a multivariate polynomial G and a field element Y. And the claim is that if you were to run G on all Boolean inputs and then sum up all the answers over a fixed field F, then the answer you get would be Y. And the name of the game here is that it would take 2 to the n time to actually decide this on your own. And the sum-check protocol allows the verifier to run this to check this in time that's polynomial in n. Okay, and yeah, hopefully most of you have seen this before. But the way it works is the prover repeatedly sends univariate polynomials that represent like what happens when you think of one of the variables of the polynomial G as actually being a variable, as being indeterminate, and all the variables to its left are set to some fixed field elements, and all the variables to its right you sum over all Boolean inputs. And then the verifier samples a field element, and this becomes the next field element that you plug into the polynomial and leave fixed for the end of time, like until the end of time. So it's a recursive protocol. Like you substitute a value for one of the variables, and then you recurse on a smaller sum check problem. Again, the details here are not very important, but just notice it requires like n rounds here because you're doing this recursive step. Okay, so I don't need to convince anybody that interactive protocols do some crazy things, but here are some crazy things that interactive protocols do. So the question for today is, to what extent do these protocols really actually require the interaction? Which sounds a little bit crazy because the protocols themselves, they seem to rely on interaction extremely heavily. And you can see this because the soundness often involves these like rewinding type arguments, for example, which is just something which only makes sense in the interactive world or in some idealized model, perhaps if you have like if you're interacting with a random oracle, for example. But we've also known that at least heuristically, it really doesn't seem like you need this interaction. That maybe the intuition that the protocols are inherently interactive is maybe incorrect. And so this is called the Fiat-Shamir transform or Fiat-Shamir heuristic. Although Fiat and Shamir originally proposed this transformation to one specific protocol, and I guess it is sometimes debated what should actually be called the Fiat-Shamir heuristic. But nowadays, what we call the Fiat-Shamir heuristic is this extremely general transformation, which takes any public coin interactive protocol and transforms it into a heuristic non-interactive argument system, where in this model on the right, the prover and verifier have common access to an efficiently computable hash function, and this hash function is completely replacing all of the interaction that happened in the original protocol. So I think Ali described this also in his talk, but how it works is you have the verifier generates the entire protocol transcript in one shot by generating the first message of the interactive protocol, and then generating each message of the interactive protocol one by one, where the prover messages can be generated because he's the prover, he knows how to do that, and the verifier messages are generated just by hashing the entire transcript prefix that has already occurred. Okay, so this is how the transformation works. And heuristically, at least heuristically, it seems like you might hope that whenever the protocol on this left-hand side is sound, that the protocol on the right-hand side is also sound. That would be amazing, and to a certain extent, this like the assumption that this is reasonable underlies a lot of practical protocols that people actually use. And it's I want to emphasize that it's particularly important, or this protocol has found such wide use because A, it's extremely general. All it needs is a public coin protocol. You need these messages, the betas, to be uniformly random, but that's all you need from the interactive protocol. That's okay. I'm simplifying a little bit. You need like a reasonable soundness error, basically, in addition. But that's all you need, and the overhead in this transformation is extremely low. All you need to do is compute a few hashes in addition to whatever you had to do before. Okay, so of course the I don't know how many dollars question is Fiat-Shamir secure? And so at least caveated with the things that I was just glossing over on the previous slide, as long as you start with a protocol which is not obviously broken, let's put it that way, then it will be secure if you model the hash function as a random oracle, meaning that if you say this, like the hash function h, just call it a uniformly random function and model computational efficiency in the query model. So you just assume that nobody can actually put their hands on the hash function. All they can do is run it on a polynomial number of inputs. Okay, and so in quite a high level of generality, we know that in this idealized model, Fiat-Shamir is secure. But this talk is precisely about how to prove security in the standard model. And the big issue, is that security of this transformation does not seem to clearly follow from any like reasonable or like to be more concrete, let's say falsifiable assumption on the hash function. That is like in theory, what we like to do is say that provided that our cryptographic building blocks satisfy some security property, some like some hopefully simple to state and well-studied security property, provided that's true, then when you use it in a protocol or in a bigger cryptographic object in some way, that's the composition is secure. That's what we'd like to say, and it's really not clear how to do that for Fiat-Shamir. Indeed, there's a very good reason for that. Namely, if you study the problem at the same level of generality at which the random oracle results are true, then you end up with counterexamples. You end up with protocols, interactive protocols that are sound and public coin, and say constant round, just to be more concrete. But such that for any efficiently computable hash function or hash function family H, the resulting Fiat-Shamir protocol is actually unsound. So in some sense, we've known about these counterexamples for a very long time, and I think like one of the prevailing like thoughts on this for a while was that, well, like it's true there are counterexamples, but the counterexamples are for protocols that like nobody would ever want to run in their life, and so maybe for all intents and purposes we can just ignore the counterexamples and everything is fine. But I would like to push back on this like intuition a little bit. It could maybe end up being true in some sense, but at the very least we'll have to be very careful, and I'm not sure whether I really believe it at all. I want to especially highlight there's this recent result of Kovratovic, Rothblum, and Sukhanov, where they say where their result is essentially take one of the most natural looking constructions of succinct non-interactive arguments that you can think of. It's like a commit and open plus GKR type protocol. So and they show that actually Fiat-Shamir for this protocol is unsound. So of course there are other variants of this protocol that we don't currently know how to break. It's not that everything in practice is broken or anything like that. That's not the message I'm trying to convey. But on the other hand, there are things that are very close to what are being run in practice right now that are broken. And so it seems quite important to understand what's going on here better than we currently do. OK, so this is a bit scary. But nevertheless, we're going to see what we can actually prove, like what, in what cases can we actually prove security. So there's been, by now, quite a long line of work over the last 5 or maybe even getting close to 10 years on this topic, which is quite terrifying because when I started working on this, there wasn't very much. And now I'm talking about 10 years ago. But so there's no way I'm going to be able to tell you everything that's happened. But so I'm going to try to give you as many short takeaway points as possible. So takeaway point number 1 that I want you to know is that all of the existing results assume that the interactive protocol we start with satisfies some form of information theoretic or statistical soundness against an unbounded prover. Now, don't take this statement quite literally. I don't mean that we only know how to compile protocols that are themselves statistically sound, but we only know how to compile protocols that somewhere inside them have some flavor of statistical soundness. And I will explain more what I mean by that later in the talk. So I guess step 1 of if all you want to do is apply current tools to Fiat-Shamir compile a protocol, then what you need to do is look for some handle of statistical soundness in that protocol. And when you can do that, the big gain you get out of this is that you can try to analyze the soundness of the Fiat-Shamir transform using this security property called correlation intractability. And correlation intractability is the security property through which essentially all known provably sound Fiat-Shamir instantiations rely on. OK, so what is this notion? Correlation intractability was defined by Canetti, Goldreich, and Halevi in 1998. And the property, very simple, very general, and so very useful to us. So a hash function family H is called correlation intractable for a sparse binary relation R, I'll explain in a second, if the following is true. For all efficient, meaning polynomial time adversaries A, there is only a negligible probability that the adversary, given the hash function H, finds an input-output pair x, y that belong to the binary relation R, such that y, the output, is equal to h of x, hash of the input. So the setup here is we have a binary relation R. There are points x comma y. We assume that the relation is sparse, which means that for every input x, there is only a negligible fraction of all second elements y belong to the relation along with x. And then what we'd like is, we say a hash function is secure in this sense if it's hard to find these rarely occurring correlations, right? So in particular, this sparsity property of R says that in the random oracle model, a random oracle satisfies this correlation intractability. So why is that? In the random oracle model, the only thing you can do with a hash function is query it on a polynomial number of points. Because it's a random oracle, every time you query the oracle on a point, you get a random y. If the relation is sparse, then with very high probability, the input-output pair x comma y that you just generated does not belong to the relation. And you can only do that polynomially many times. And if you don't find an R correlation with your polynomial number of queries, then you've failed. So this sparsity property says that you'll at least get correlation intractability in the random oracle model, and then the whole paradigm that we have for instantiating Fiat-Shamir is by giving standard model instantiations of correlation intractability and then using it to analyze the Fiat-Shamir soundness of non-interactive, of protocols you obtain by applying the Fiat-Shamir transform. I think I'm going a little bit quickly, so please stop me if you have any questions, or maybe you know this already. But...
You can always finish early.
Sure, yes. Yes?
So in this case, the random oracle is like the H, right? That's given to
Yeah, if you want to do a random oracle analysis, then yeah, you'll model this H as a random oracle.
Why can't the adversary just like pick an X, give it to the random oracle, get the Y, and output that pair?
That's the best. That's essentially the best thing you can do. You can try polynomially many times, but in order to break the hash function, to break the security property, the input-output pair x comma y has to belong to this unspecified relation. So, for example, you can think of the relation, like if the input and output have the same length, you can think about the relation like y equals x, right? Yeah. So for the y equals x relation, the security property would say that it's hard to find an input x such that hash of x equals x. And so yeah, when you query the random oracle, you're not going to find an input with this property. And indeed, for any relation with this sparsity property, you are unlikely to succeed. Yes?
Is the sparsity definition a for all x there are a few y?
That's right.
Okay, so would, I don't know if you can answer this, but would be the effect of there are a few x that can have a lot of y's, but they're like a negligible amount?
Well, let's say the adversary knows which x these are, right?
Mm-hmm.
Then they can just focus on looking at this set of x. For example, like even let's think of it an attack in the random oracle model, right? If it's easy to if it's sort of plain to see which x have these many y's, then you can just query the hash function. You can run the hash function on only those x's, and you're much more likely to find a correlation. Like another way of putting it is that this security, like you break security here, no matter like what distribution of x this is. We're not looking for like a random x along with hash of x belonging to the relation. Even if like x is always the all zero string, and it happens to be easy to find to break this on the all zero string, then it's broken.
Sure, I guess there might be some relations where you can't know.
Yes, but indeed. So you can talk about
family of relations.
Yeah, you can talk about like notions of computational sparsity, so to speak, right? Where maybe it's not sparse, but it's hard to witness the fact that it's not sparse, right? Unfortunately, the results I'm about to present don't really handle these kinds of relation families, and there's good reason for that. You're going to get so although random oracles will satisfy correlation intractability for this kind of like not exactly relation, it turns out there will be lots of standard model counterexamples like there are for Fiat-Shamir. So when you think about correlation intractability or that kind of relaxation of correlation intractability, you end up with a cryptographic task which is about as hard as doing Fiat-Shamir for all arguments.
So
yes.
in the standard model, it's clear that R cannot depend on H, but can H depend on R?
So, 1 second. Let me. R cannot depend on H. So that's actually not so, okay. Sorry. By H, do you mean that the hash function or the hash function family? There's a hash function family,
so
and then you sample a hash function. So certainly nothing can depend on the hash function that you sampled, but the relation, for example, could depend on the hash function family.
But can R, so you want an H, so you're given R, you're fine with finding an R specific H?
Yeah, so it's very application specific. Sometimes we are and sometimes we aren't. Yeah, we need to scope in order to answer that question. Okay, but this is the this is the main security definition that we're going to care about for the rest of the talk. Okay, so I mean, I kind of just drew this definition out of nowhere, though, right? It's not immediately clear. I started with Fiat-Shamir, and then I gave you this definition. If you haven't seen it before, it's maybe not obvious why exactly this corresponds to the security of Fiat-Shamir. Of course, it hopefully looks like a useful property to have, but let's make the connection extremely clear by arguing that if you have correlation intractable hash functions for sufficiently expressive relations, then you can provably Fiat-Shamir compile any 3-message public coin proof system. So 3-message public coin protocol that is information theoretically sound. This can be generalized to more than 3 messages, but then the words on the slide, I would have to decrease the font size on the slide, which would not be good. Okay, so let's argue soundness here. So we're starting with an arbitrary protocol on the left here, which satisfies information theoretic soundness in the interactive model. And what does that mean? It exactly means that when the initial statement X is false, what we know is that for every first message alpha that the prover might send to the verifier, if the verifier samples its message, beta, uniformly at random, then with high probability, the prover is unable to trick the verifier into accepting afterwards. So this is just a restatement of what soundness means. I haven't done anything yet. But the key insight here is that although this soundness property is talking about somehow all 3 messages, right? Like what happens in all 3 rounds of the protocol, it turns out that you can actually sort of forget, in some sense, forget this 3rd message gamma that the prover is sending, and reduce from a security property that is kind of only referencing the first 2 messages, alpha and beta. And this is the like key step which absolutely does not work when this protocol is only computationally sound. It's really using the information theoretic soundness, yeah, we can talk more about it afterwards, but just something to keep in mind.
So, maybe you can articulate more what you meant by saying that it doesn't involve gamma. I don't understand.
Yeah, so I'm about to right now. So the idea is the following. Let's define a relation. Remember, we're talking about binary relations, right? We have 2 arguments. So the first argument of the binary relation is going to be the first message alpha, and the second argument is going to be the second message beta. So we're going to think about relations on alpha-beta pairs. So of course we're not going to completely forget like the protocol, but the point is that the relation is is talking about alpha, like first message, second message pairs. So where gamma comes in is in the definition of the relation. So for every false statement X, you can define what I'm going to call the bad challenge relation for this protocol and this input X. Message pair alpha beta belongs to the bad challenge relation if it is possible to information theoretically trick the verifier in the protocol, provided that alpha and beta were the first 2 messages. Is that a question?
Yeah. Why is it X fixed?
So,
Why do you need X fixed?
there are 2 sort of equivalent ways of doing this. You could instead have a single relation where X and alpha together are the first arguments, and I just didn't do that because I thought it looked nicer this way. But you could also instead of doing this, I could have a single R where the first argument is X comma alpha and the second argument is beta. And then in this relation, what you would this tuple belongs to the relation if it's possible for the prover to cheat and the statement X is false.
Can you achieve adaptive soundness with X fixed like that?
No. So yeah, this is for obtaining non-adaptive soundness, and this other thing that I just said is what you do if you want adaptive soundness. But yeah, apologies in advance. I'm not going to distinguish between non-adaptive and adaptive soundness in this talk. There are we have ways of talking about adaptive soundness, but it's I'm not going to talk about it. Yes.
So here, like, it's a relation, not a language, right? So like, the corresponding language would be alpha is in the language if there exists a beta such that there exists a gamma such that something?
So that would be if you're thinking about this as like an NP relation or something, yeah, something like that. It turns out this is not, yeah, you could do that, but this turns out not to be the most meaningful thing to do if what you want is soundness of Fiat-Shamir. Like, yes, you could do it, but often the way it turns out is that every alpha is in the language. Like there will be like maybe one beta that belongs to this relation along with alpha. But what we're using is the fact that there aren't very many betas.
So it's like, so the fact that it is a relation is because you want for the correlation interactability, you want the second term to be like a hash of the first one, but not in the NP way. There's like,
yes.
It's a two-term thing.
So, yes, that's exactly right. Yeah. Okay, so in some sense, this is the key definition for understanding everything that's about to happen. So yeah, please ask more questions if this definition doesn't yet make sense. Yes?
Can we find gamma in polynomial time?
Not necessarily, and indeed, like for for your favorite protocol, you might expect that maybe it's not possible. It really depends. It's not clear, but what we're this will come up in a moment, and basically, yeah, what you're asking is equivalent to the question of, like, can you decide, given an alpha and beta, is it easy to decide whether or not they actually belong to this relation? Right? That's, yeah. Can you find gamma in polynomial time is basically that question. Yeah, and in general, the answer is definitely no. Even for like nice protocols that you start with, the answer is often no. And this is a huge challenge for provable security because, for example, like correlation interactability for a relation R is only a falsifiable cryptographic assumption. You can only tell if it's broken if you can actually decide this relation membership in polynomial time. And so, yeah, I'm getting ahead of myself, but you really do want to end up in a situation where you're working with relations whose membership you can decide in polynomial time. And it's not yet clear why that should be. But yeah, in general, the answer is definitely no. You should think of this as being a very inefficient relation. Okay, so here's our bad challenge relation. With all the setup so far, probably you can predict what I'm going to say next, which is notice a couple of things. One, if the hash function family is correlation intractable for these bad challenge relations, then when you apply Fiat-Shamir using this hash function family, you will get a sound non-interactive argument. And the reason for that is because we have exactly set things up so that if the Fiat-Shamir verifier accepts, so if it accepts a first message alpha, second message hash of alpha, and third message gamma, then it must be the case that the pair alpha comma hash of alpha belongs to the relation because there exists a gamma making the verifier accept. I didn't say this, but the fact that the protocol is sound in the interactive setting exactly says that these relations are sparse. Right? It says for every first argument with high probability over the second argument, the pair does not belong to the relation. There does not exist a way to make the verifier accept. Okay. So this says that if you have correlation intractability for example, all sparse relations, then you can Fiat-Shamir compile any three-message interactive proofs, public coin interactive proof. And moreover, you can extend this analysis, it turns out, to any constant number of rounds. Although I think it really shouldn't be obvious based on what I've said so far that you can do this. But one way to see that this extends to a constant number of rounds is to go through this notion of soundness of interactive protocols called round-by-round soundness. And I don't want to go through the definition, but basically what it says is that a protocol is round by round sound if there is basically an invariant or a property of partial transcripts of the protocol that is hard for the prover to escape when going from one round to the next. Right, so you kind of set up a game where the prover is trying to escape some property, and if the property is hard to escape for the prover, then the protocol is round by round sound. And somehow this like hard to escape a property kind of statement is something that's very amenable to correlation and tractability. Yes?
Is this limitation to constant rounds just based on like round by round sound? Like the fact that round by round sound gets weird with super constant rounds, or is there something?
Yes,
like
that's it. So correlation and tractability exactly allows you to Fiat-Shamir compile protocols of any number of rounds, provided that they satisfy this round by round soundness that I'm hand waving here. And it just turns out that every constant round protocol that has negligible soundness error also satisfies this round by round soundness property without loss of generality. But in the super constant number of round setting, some protocols don't. But those are the protocols where you can't even Fiat-Shamir compile on the random oracle model. So everything is everything is reasonable.
And is the round by round soundness necessary for these processes, or can you get, for example, in the random oracle, you can use state restoration instead?
Those turn out to be equivalent.
Okay.
Yes.
In any setting or in the constant round setting?
No, in any setting. I'm throwing away some, like various, it's maybe not tightly related, but.
Could you do it? Sorry.
Could you maybe say a bit more about what would break if the original protocol is only computationalist?
Yes. So, sorry, go on. In a computationally sound protocol, you can define this, right? There's nothing stopping you from writing down this definition. The problem is that this relation might just be everything. It might be that no matter, for every possible message the prover sends first, for every beta the verifier sends back, that there exists a message that would make the verifier accept, but it's just computationally hard to find this gamma. That's a lot of, you can think of a lot of computationally sound protocols as being more like that.
Actually, they are like that. That's the definition of computational sound, that it's hard to find. It exists,
that's all computational soundness guarantees you. Yes, and then a lot of computationally sound protocols in the wild will really behave like that. And then this relation is just literally everything, and it's not sparse, and this framework it's not clear that it's useful.
And do you think that there could have been a relaxation of this bad challenge relation, which would work for computational sound?
Yeah, so I think this is similar to another discussion that we were having a few minutes ago, which is you can talk about relations that aren't sparse but satisfy some computational analog of sparsity. And I think it's a great idea to think about this more. But if you define this too generally, you will go back to hitting the Fiat-Shamir counterexamples, and then it will be impossible to satisfy this kind of property. But I'm not at all, there may well be some reasonable intermediate notion here, and I think this is a great research direction, but I can't tell you much right now.
Alex?
Yes.
Returning to the earlier question, I'm also curious. So round-by-round soundness and state restoration are asymptotically equivalent, though in the concrete parameters, not quite.
Yeah.
Would correlation tractability also, let's say, very neatly work natively for state restoration without taking the implication to round-by-round soundness? Or
I doubt it. I think that correlation and tractability matches up quite tightly with the round-by-round soundness, and I don't immediately know of direct arguments that doesn't go through round-by-round soundness as an intermediate.
Do you think it's plausible that there is maybe some maybe relaxation of the notion of correlation tractability to be maybe something less beautiful, maybe? Because anyway, state restoration is less beautiful than round soundness, so we have to give up on that. but something that nevertheless.
Yeah, I think that's a very good idea. Actually, I haven't tried to do this, but yeah, there may be some variant of correlation and tractability that's more tightly related to state restoration soundness, but it will not. I do not think that's off the shelf that this will do that.
That's reasonable, because if it's tightly coupled round soundness, and round soundness is not tightly coupled,
Yeah.
then
Yeah. No, but this is a very good idea. Okay. Yeah, so I guess, well, we had a somewhat extensive discussion on this already, but yeah, because you can, correlation and tractability is not just useful for compiling constant round protocols, but any protocol satisfying this round by round soundness notion, and therefore, it turns out you can also apply it to the sumcheck protocol and to other information theoretic protocols that are built out of the sumcheck protocol, which is great. I don't want to spend too much time talking about it, but it turns out that there is a very natural notion of what it means for a challenge to be bad in the sumcheck protocol. If you remember, the sumcheck protocol is recursive. The prover sends a polynomial. The verifier sends an input, like a univariate polynomial verifier sends an input. And it turns out that the bad challenges are exactly the field elements such that if you evaluate the polynomial the adversarial prover sent you on that input, that it happens to match the evaluation of the polynomial the prover was supposed to send on that same input. So this is just up here for fun, but yeah, take away bad challenge notion for sumcheck is very natural and reasonable. Yes?
Quick question. So you mentioned that the analysis extends to any constant number of rounds. The sumcheck protocol scales with the number of variables, so it only works for a constant number of variables. Is that correct?
No. So this you can analyze Fiat-Shamir applied to the sumcheck protocol with any number of rounds.
Okay.
You can't do this there are super constant round protocols that are not amenable to Fiat-Shamir, but sumcheck is, and so we're fine. Yes.
So what's an example of a round-by-round protocol that isn't sumcheck that I should be keeping in mind?
No. You're only allowed to you have two favorite protocols.
I'm saying if I came up with the constant round thing, it would also apply, but there's no
No, so okay. So a less memey answer is that just think about other protocols that have recursion. When a protocol which sort of recurses on itself is typically going to be a super constant round protocol that satisfies some round by round soundness notion. So for example, in the CJJ batch argument, that exactly happens. At least some versions don't use sumcheck anywhere, but they still have this recursive structure. Okay, and yeah, so we already discussed this, but you may notice that we might usually like to think of relations as being efficient objects, like something that where you can verify whether something belongs to the relation in polynomial time, but in general that may not be the case. There's actually no reason a priori why that's the case here. Okay, so if we had correlation and tractability for all sparse relations, we would be done. In the sense that we could Fiat-Shamir compile any statistically sound proof. We wouldn't be done with building snargs for NP. That would still be open, but we would have a lot of results. We'd be pretty happy. Unfortunately, so you might ask if it's actually possible to do this. So there is actually a pretty major caveat here that maybe people forget about sometimes, which is that depending on how you define correlation and tractability, this is actually also subject to counterexamples. I don't want to spend too much time on it, but if you think about some universal computation U, it turns out there's this really annoying relation R, which says that input-output pair alpha beta belongs to the relation. If beta happens to be what you get when you interpret alpha as the description of a computation, like a Turing machine, for example, and then run it on its own description. So it's one of these diagonalization arguments. And so exactly the issue is that, so this relation is sparse, right? Because for every alpha, there's only one beta, which belongs to the relation with it. But for any hash function h, you can break correlation intractability of h with respect to this relation because you can always say, well, look, I'll set alpha to be the description of the hash function itself, and beta will be what happens when you run the hash function on its own description. So this beta is equal to hash of alpha, but it's also the relation point. And so this is actually an attack on correlation intractability. So this might look actually very scary, but it turns out it's not too bad. Like the conclusion that you draw out of this is that if you want something that's correlation intractable for all sparse relations, you can only do it in this restricted setting where you can allow the hash function description to grow with the input length of your relation, which is actually somewhat weird, I think, if you're a practitioner, because you're hashing like an entire protocol transcript in Fiat-Shamir, including like your original instance, and now I'm saying, hey, look, your hash function description should be longer than that. That's kind of weird, but nevertheless, like in theory, this is what you need. Although, like, this is what you need if you want correlation intractability for all sparse relations. Nobody says that it has to be this way if you want to focus on a more specific relation class.
But still scary enough to deter people with 20 years.
Yes. Ron did a very good job of scaring people. Ron, did you want to say something?
No, just but since you asked, then I think this is really the source of our recent attack also on GPR.
Yes. Yeah. Yes. The attacks on Fiat-Shamir for interactive arguments are also using this kind of diagonalization type.
More than that, it's that the hash function is not growing with.
Oh, I see. Yes. Okay. That's a good point.
And this in practice would be very costly. Yeah.
Okay, so subject to this caveat, however, it seems like there's nothing stopping us from building a hash function with this property. And indeed, if you make extremely strong computational hardness assumptions, it's known how to build hash functions satisfying this super strong form of correlation intractability. So if all you're looking for is a justification that like you're using a not false security property, this is already quite good evidence. If we're theorists, we'd like actually even more than that. We'd like to rely on hardness assumptions that we actually understand, or hardness assumptions that are well studied or even standard, hopefully. And here we're still maybe a little far from being able to do this. I want to briefly mention that Rahul Longo and I have a recent work that contains maybe interesting results on this topic, which says that if you assume, so the question here is is there any reasonable assumption you can write down that will give you correlation intractability for all sparse relations? And the answer is if you assume sub-exponential I/O, very strong, but at least something that people have thought about before, and you consider an obfuscated pseudorandom function, which is sort of the canonical candidate correlation intractable hash function, then an obfuscated pseudorandom function will satisfy this really strong security property, provided that, under a certain worst case hardness assumption that's starting to look more in the realm of complexity theory than cryptography, although I would really place it somewhere in between the two. But instead of thinking about correlation intractability, you can think about worst case computational problem, very directly corresponding, called correlation finding, where the input to your problem is a circuit, and the output is supposed to be a correlation for the circuits. So the input is C, and the output is alpha comma beta. And you solved the problem if for every C, you find an alpha comma beta such that beta is equal to C of alpha, and alpha comma beta belongs to the relation. And so what we show is that if for all sparse relations, this worst case problem is hard to solve in polynomial time, then an obfuscated pseudorandom function will be correlation intractable for all sparse relations.
Can the results in the first bullet, the concrete results, be derived as corollaries of the second?
I'm sorry, can you say that again?
Can the results you mentioned in the first bullet, the concrete results, be derived easily as corollaries?
No, it's not clear. Yeah, of course, implicitly these strong assumptions are implying that this worst case problem is hard, but it doesn't seem to be a natural factoring of the results.
Yeah, the IO part is.
So what is the order of quantifiers in the white bulk correlation finding is hard?
It's if for all sparse R, so for every sparse R, there is a white box correlation finding problem that's defined with respect to R. So if for all R correlation finding is hard in the worst case, then for all R, an obfuscated PRF is correlation intractable for R. Or then an obfuscated PRF is correlation intractable for all sparse R.
Question. Does the result factor in the sense that, let's say that I don't want to capture all sparse relations, but only set given?
Yes. So,
can I then embed that set in the worst case problem?
Yeah, I'll mention one instance of this. So the answer is depending on your set of relations, maybe. Like for certain kinds, yes. For example, if you restrict to relations that you can decide in polynomial time, the results holds when you restrict to this relation class. In general, what the result does is for every R that you want correlation intractability for, there is a specific relation R prime that you want the worst case R prime, the worst case hardness for. It's not equal to R, but it's a specific relation that's related to R in a not crazy way. Anyway, so here's one more interesting thing we know about correlation intractability for all sparse relations. Where? Sorry. Oh, hi.
What are these strong assumptions? Sub-exponential I was the step down.
For example, a point function obfuscation scheme where you can obfuscate like oh god, I don't want to do this, but yeah. But if you want to, but one thing to keep in mind is like it's assumptions that say there's no algorithm for a problem better than brute force / naive guessing, and it involves like a form of circular security or a key dependent message security where the relationship is like computationally inefficient. So what Yael said. All right, I want to say a few more things, so I'm going to start going a little bit faster to wrap up. So we would love to be able to just say that we can build correlation intractable hash functions for all sparse relations from a standard assumption. I think it's a great open problem. I don't think that it's crazy that you could do this. I think it's a reasonable thing to try to do. We don't currently know how to do it, and so instead what we do is we instantiate Fiat Shamir on a very case-by-case basis by following by taking the following two steps. We say, all right, for a particular protocol pi that we care about, we'll show that Fiat Shamir for pi is sound, provided that the hash function is correlation intractable for simple-looking relations R sub x, not necessarily the one that I wrote down before, because we're free to choose the there isn't a single relation for which that theorem is true. You can there are many relations such that correlation intractability for R will imply soundness of Fiat Shamir. So let's pick a simple relation. Often this requires tailoring the protocol so that correlation intractability for simple relations really does govern the security of Fiat Shamir for that protocol. And then we have to construct hash families that are correlation intractable for these sufficiently simple relations. And the main idea here is exactly to focus on relations such that deciding membership can be done in polynomial time, which is hopefully doesn't sound crazy. It seems very reasonable that these are the kinds of things we'd be able to build from standard assumptions more easily. However, we actually don't even know how to build this kind of correlation intractability from standard assumptions, just for all sparse relations whose membership you can decide in polynomial time. And I think that is a fantastic open problem that hopefully one of you will solve soon. And yes, this result with Rahul that I mentioned also applies to this class, but of course you can hope for a way better result statement than this. Okay, so if like relations whose membership you can decide in polynomial time is too much, we can focus even further. You can just consider relations such that every first argument has a single second argument belonging to the relation along with the first one. So these relations are what are called functions, right? Relations with the unique output for every input is exactly a function. And so it turns out that we can build, under standard assumptions, correlation intractability for all functions that are computable in a bounded polynomial time. We had a result doing it from circular secure FHE, and then Pikert and Sheehan improved this to rely just on plain LWE. So this is something that you can do based on LWE. I do want to highlight one major drawback of what we know how to do here, and this is true for all of the other correlation intractability results that we know, which is that the complexity of hashing, like for the hash function for which we can prove security, the complexity of hash function evaluation has to grow with this bounds on the running time of the function f that are supported in this definition. So if you want to avoid functions f that take time t to compute, you have to run a hash function that takes time greater than t to evaluate. And there's no reason a priori that our constructions have to be like this, but this is a barrier that we have, as of yet, not been able to overcome. I do not want to go over the proof of this theorem right now because we don't have much time. But here is basically what we know in terms of instantiations of correlation intractability based on standard computational assumptions. So 3 of these results are just for functions and not relations that are not functions. One of them, this results with Justin and Ron, we show how to handle, I'll flash a slide for what a product relation is, but we can handle relations that are not functions that have a particular structure that conveniently turns out to be the main thing that comes up when you want to Fiat-Shamir compile protocols. So we don't know how to handle like all functions whose membership you can efficiently decide, but we can handle a really large class of relations that matter to us in the practice of theoretical cryptography. So we have results based on LWE for the complexity class of all polytime functions. We have this result of Jane and Jin, which says that if all you care about is correlation intractability for functions that have low threshold circuit complexity, this TC0 class, then you can do it based on the hardness of DDH, the Diffie-Hellman assumption. And there's this really cool result actually from last year of Dao, Jane, and Jin, where they inside it, they show that if you care about really, really simple functions, then you can do it based on the hardness of solving multivariate quadratic equations, which I think is nice and worth highlighting because unlike these results, this assumption is not known to imply public key cryptography. And a hash function is not normally something you think of as being something that requires public key cryptography. And this is the only result I'm aware of that really actually achieves this here. I'm going to take a couple of minutes to wrap up. Is that OK? So this is the correlation intractability sort of side of what we know how to do. Yes. So it suffices for a NIZK if you additionally assume LPN. So they exactly using their approach. Yes.
LPN in a high noise regime that does not imply PKE, or in a low noise regime that doesn't imply PKE?
Okay, I could be getting it wrong, but I think that none of the assumptions in their NIZK imply public key cryptography, but I could be getting it wrong. You're right. So okay, let's take it offline so I don't say false things. Okay, so let's say a brief word on what these restricted notions of correlation and tractability say about Fiat-Shamir. Why this because before we started we said you could do Fiat-Shamir if you had correlation and tractable hash functions for relations that were not easy to decide. So let's quickly see why you can hope to argue about Fiat-Shamir using this weaker form of correlation and tractability. So let's think about one of the two favorite protocols, the commit and open protocol. And let's think about how you would argue soundness of Fiat-Shamir for this protocol specifically. So the key idea here is to think about a slightly different relation than the one that we talked about before. Before we said alpha beta is in the relation if there exists an accepting third message. Here I'm going to write down something different. Here I want to say, so first of all, okay, the first message, quote unquote, here is this message, alpha, which is a commitment to a string. And the verifier sends back a set of locations that they want to see. So I'll say that alpha and this set S belong to the bad challenge relation if you were to look inside the commitment and look at the underlying message, right? Just like this is a bitwise, say, commitment to a vector. Let's say you look at what the message is, and then you look at the message, you look at the string restricted to the set S, and then you think about what the verifier would be checking over here if you actually opened that string. Alpha comma S belongs to the relation if the verifier would accept that substring. In other words, the substring that you are forced to open to, that you would be forced to open to in this protocol. So notice the kind of argument that I'm making is assuming that the commitment is statistically binding, and if the commitment is not statistically binding, this makes no sense. And indeed, you can't argue Fiat-Shamir in that setting. So this is pretty similar to the relation before, but it's thinking a bit more about the structure of the protocol and saying specifically about this step of looking inside the commitment. But hopefully it's not hard to see that correlation and tractability for this relation also implies the soundness of Fiat-Shamir for this protocol. So now there are two ideas which gets us from here to provable instantiation. Idea number one is that if it so happens, and this is a big ask actually, but if it so happens that every alpha has a unique S that belongs to this relation, or at most one S that belongs to this relation, then the bad challenge relation is a function. This is pretty tautological. I'm saying if it's a function, then it's a function. Actually, this argument extends to when you have a few bad challenges by some sort of guessing reduction, and it extends to many bad challenges if they satisfy some combinatorial structure that I don't have time to discuss. Now the second idea, which is, remember, we care about the efficiency of the relation, but so the second idea is that if this commitment key happens to have a trapdoor that allows you to efficiently extract the message from the commitment string. So many commitments have this property, although this seems to be using some sort of public key cryptography. But if your commitment has this property, then the bad challenge relation, which was also a function, is also easy to compute, because the only inefficient operation here is this step of saying, take the commitment string and look at the underlying message. So if there's an efficient way to extract this from the commitment string, then this relation in its entirety is efficient, and then you can prove soundness based on standard assumptions. Okay, so I don't have time to talk about this stuff beyond functions, but one sentence on this is that you can go from functions to things that are not functions by using coding theory. So the idea is that you can, instead of just having a correlation and tractable hash function, you can think about a composition which applies a cryptographic hash function to your input, and then afterwards applies some error correcting code, treating this as a message and encoding it using an error correcting code. And the idea is that this basically allows you to reduce from you can show that this composition satisfies correlation and tractability for relations that are not functions, provided that this is correlation and tractable for functions, and this is a good enough error correcting code. Okay. 1 second. Yeah, and basically what this lets you do is handle protocols whose soundness you obtain through parallel repetition, which is very useful because a lot of protocols are obtained in that way. So finally, one particularly important application that I want to mention, and you'll have to go to Omer's talk on Wednesday for more information on what this is used for. But there's this work of Chaudhary, Jain, and Jin, which had this really cool idea about how to apply Fiat Shamir to an important protocol, which is not information theoretically sound, but only computationally sound, and you're getting a really interesting succinct argument out of it. It's not a succinct argument for NP. What it is it's a somewhat succinct argument for this class of problems called batch NP. So the situation here is if you imagine you have many NP statements that you want to check, and the prover has an NP witness for every single one of these statements, we'd like a succinct argument that convinces the verifier that simultaneously all of these case statements are true, where the amount of work the verifier has to do to check this can grow with the length of one witness, but should not grow with this parameter k. So it saves you work in the batch setting where k is large. Even for this restricted kind of problem, it's known that you can't have an information theoretically sound protocol, at least it's suspected that you can't have an information theoretically sound protocol for this task. But there's a very simple, reasonable-looking, computationally sound protocol for this task, where you run Killian, but we don't run Killian for the batch computation. You can think about running Killian for each of the k computations separately, and sending a commitment which is called somewhere statistically binding. So in the Killian protocol, you would just send like a security parameter length commitment here, right? But instead, these folks consider a protocol where you consider a commitment that grows with the length of a single proof, but not with the parameter k. And the advantage of doing this is that although this commitment is only computationally binding, it can be statistically binding on a single one of these proofs. Right, so somewhere statistically binding is some security property that says that depending on how the key is sampled, this commitment scheme is going to be binding on one of the k proofs, an unknown one of the k proofs. And the point, I know I'm hand-waving this a lot, but the rough idea is that you can argue about the security of Fiat Shamir for this protocol even though it is not statistically sound, because for every false statement, there is a choice of commitment key that the verifier could have made, such that if you restrict the prover to working with this particular false x sub I, then the protocol will become information theoretically sound. In other words, if you have a commitment scheme which is only binding on a certain subset of locations, and you have some constraint on the prover saying that they have to lie on this subset of locations, then suddenly, in a hybrid argument, you are working with an information theoretically sound protocol again. So I understand this is not a proof. Just take this as impressionist artwork of how the CJJ proof works. But the idea is that even if it seems like you're doomed and you don't have an information theoretically sound interactive protocol to work with, sometimes if you hope hard enough, then you can analyze things based on correlation and tractability anyway by sort of identifying a piece of the protocol that is information theoretically sound. And so, using this, through this overall paradigm that we've been talking about today, we've gotten a bunch of really cool results over the last few years, including new constructions of non-interactive zero-knowledge arguments, constructions of succinct non-interactive arguments in the batch setting, which have been applied to give other succinct non-interactive arguments through additional techniques that Omer will tell you about on Wednesday. And like, yeah, again, the main takeaway of the talk is that's like through all the things that I've said, we have this nice flow chart for like what Fiat-Shamir instantiations we know how to do and what are the good open directions for future work. And yeah, there are basically a few questions that matter, like is the protocol statistically sound? Is the bad challenge relation efficient to decide? How many bad challenges are there? And how hard is it to compute what they are? Like in what complexity class do they live? And so you can stare at this flowchart later, and maybe it'll be useful in your research. I think I've described these open problems already, so I won't state them again. I guess the one thing that I haven't mentioned is that it's really not clear what's going on with respect to Fiat-Shamir for like general purpose arguments. I think Gal is going to give a talk related to this later in the week, and I encourage you to think about this problem, because in full generality, I don't expect correlation intractability to be exactly the right security notion for Fiat-Shamir. Anyway, thank you for listening.
Essential.